picture here. We have the 4 right-hand corner rectangles. There's also a third option in the middle there where the height of the rectangle is determined by going exactly halfway in the middle of the interval and drawing the line straight up there, and then your function is about halfway between the left and the right-hand corner. Okay, so that's a midpoint version. Now on the right-hand side, on that column over there, you'll notice that when we bump up the number to 10, a little more than 8 even, we bump up the number to 10 and we're using left-hand corners. Well, that's a reasonable approximation. But if we add more rectangles, if we go to 50 subintervals and make 50 rectangles, then you get an even better picture. And I wouldn't recommend doing this by hand, but if you break up the interval from 0 to 1 into 500 subintervals, like the very last one,
Sounds fun.
so 1 over 500 is the width, then you have super skinny rectangles, but the amount that you're over or the amount that you're under is significantly less. So when n is equal to 500, it nearly looks like we're approximating the curve itself. And so the more rectangles we have, the better our approximation should become. And if you look closely, it doesn't come in very well, but on n equals 50, n equals 100, and n equals 500, there's a calculation at the bottom that tells you, okay, you've got the estimated area and the actual area. It turns out that the area under y equals x squared from 0 to 1 is exactly 1/3. And those numbers, the estimated areas, are getting closer and closer to a value of 1/3 as you add more and more rectangles.
So how did they figure the actual area?